Okay, so the whole idea here is that you can approximate actual values with estimated values, which are the differentials. The actual change is f of x plus delta x minus f of x. We call that delta y. Now, since the actual change can be estimated by the differential, we know that that estimated change is equal to the derivative times the differential. Okay, so what is this used for? It's used to estimate something called propagated error. Differentials are used to estimate something called propagated error. Propagated error is what happens when you are working with estimated values and you want to know how they affect your calculations. So let's say you're an engineer and you're working with some estimated value. You want to know how that error propagates through your calculations. I cannot spell propagates, apparently. Okay, and we're going to explain this with a nice example. Okay, so in the real world, you go and you measure stuff. Okay, come on, computer. Let me draw a square or a rectangle. Okay, here you are. Let's say you're an engineer and there's something that you're measuring. Okay, are measurements ever perfect? No. Yeah, they'll be close, but they're not going to be perfect. So let's say that you're working with a square here. I'm going to try to make it a square, whatever. You know that it's a square. Okay. So you go and you measure one of these sides. Let's make that green. Okay, I wanted green. Okay, you measure one of these sides right here. And you measure it as length x. Now here's the problem. When you measure something, you don't ever get a perfect measurement. There's something called a measurement error. Have you taken a physics class where they tell you like, oh, your instrument is only accurate to win whatever amount? So we're going to say that your measurement error is 0.1. And let's say we're measuring in centimeters. So let's say that you measure the side of this square as 5 centimeters. Okay, now, because you have a measurement error of 0.1, what might actually be the true length of the side? Exactly. So the idea here is that the actual length might be x plus delta x, which would be 5.1 centimeters. And then you'd get like an exaggerated thing that would look like this. Or maybe you were delta x in the other direction. That would be x minus delta x. It could be as small as 4.9 centimeters. And then you're going to get something that looks like this. Obviously super exaggerated, yes? So you measured a side. And let's say that you were measuring the side to calculate the area. If you're calculating the area, you're going to take your side and you're going to square it. Does everyone agree with that? Now the question is, because you measured the side incorrectly, that means that you're also going to get an error in the actual area. That's what we mean by propagated error. You're going to take your measured side, use it to calculate an area, and because you calculated the side incorrectly, that means you're also going to have an incorrect area. The propagated error is usually what we call delta y. And we just found that delta y can be approximated by the differential dy, which we found out was equal to f prime x delta x. or f prime x dx. So this is what you're going to do. You are calculating area. Area is x squared. You now want to know, hey, what is the actual amount of air that might be possible for the area that I calculate? That's delta A. Delta A is going to be approximately equal to the differential of your area. The differential of your area is equal to the derivative of your area times dx. And the differential dx is the same thing as delta x. Delta x was our measurement air. And what did I say the measurement air was in this case for our instrument? Right, so delta x is now going to be replaced with 0.1. And now I need to know what my derivative is. Well, if my original function, my area function is x squared, that means my derivative function is 2x. And then what was the x value that I encountered as my measurement? The actual measurement. Yeah, exactly. So my derivative at 5 is 2 times 5, which is 10. So that's what I'm going to plug in right here. And this is all in centimeters. So 10 times 0.1 is 1. That means the propagated air, or the air I might have in my measurement, this is centimeters times centimeters, so centimeters squared. This is telling me, even though, and I'm going to write this out, I can't say. Even though my measurement of the side was accurate to 0.1 centimeters, I have a propagated air of 1 centimeter squared for the area. In other words, even though I was accurate to measuring the side by 0.1 centimeters, the area that I end up calculating of 25 square centimeters might be off by as much as 1 square centimeter. So this gives you an idea of like, okay, cool, I'm measuring a side, I'm going to use that to calculate an area. How does my air in calculating the side, how is that going to affect the area that I calculate? That's what that value gives you.